Hello, everyone. Happy Friday. We have made it through the first week of COVID semester. Congrats. Give yourselves a pat on the back. Some reminders about this class. Homework 1 is due, Kappa 1 is due at 5 o'clock today. I got online this morning and saw that most of you have finished it, but some of you have not. So time is running short. Do finish that. Also, I didn't check the response results on this, and I forgot to remind you on Wednesday. Reflective writing 1 is due at 8 p.m. this evening. It will always, so that's an unusual time for both of those. In the future, almost always, Kappas will be due Thursday at midnight-ish, Thursday just before midnight, Thursday night. And then the reflective writing will be due Friday mornings so that I can compile them and talk about them in class on Friday if we need to. The idea is, as soon as you finish your Kappa set, you can go on and do the reflective writing. Again, it shouldn't take you any more than 10 minutes or 15 minutes to do. So hop on and do that. Again, what am I looking for? A couple sentences, just answer the questions thoughtfully, and that's all I'm really looking for. Questions about Kappa or Canvas or other course logistics? What I forgot to put up was the attendance thing. I actually have 0 people attending on Zoom today, which is interesting. Okay, the attendance is up now. Take a minute to do that real quick. So we know who was here. So the provost knows who was here today. Great. There it is. We spent Friday talking about this document, Greatest Hits of Analytical Physics 2. We're going to continue with this document with the other important law that's on here that we haven't really talked about yet. So we talked and did a problem on Faraday's law on Wednesday. We're going to talk about Ampere's law today, and not only Ampere's law as you've seen it before, but Ampere's law with a bonus section, which you probably haven't seen before. So let's talk briefly about Ampere's law. If you haven't done the attendance thing, please do that. So here's Ampere's law. Loop integral of B dot ds is equal to mu naught times the enclosed current. This is what lets you calculate what the magnetic field is around and that is induced by an actual charged particles moving through a wire or moving through space or anywhere else, right? You probably did problems in Analyt 2 or Physics 2, your Physics 2, where you did exactly that. And that's important, but we're not really going to be concerned with this part of Ampere's law. There's actually a second part to Ampere's law, which has another name. This is Maxwell's law of inductance. Close this attendance thing now. Okay. And it is a simple add-on term to there we go. A simple add-on term to Ampere's law. So it's also the magnetic field can be due to a charged particle moving, can be due to a current, It can also be induced by a changing electric flux. So here is the added term. You've got some constant, mu naught epsilon naught, and then you've got a term which is going to look very familiar to you. D phi E dt. Phi E is almost completely analogous to phi B. It is the flux of electric field. Very similar to the flux of magnetic field from Faraday's law. This is very much analogous to Faraday's law. If you take out and don't look at, if you just take Maxwell's law of inductance and take Ampere's law out of it, say there's no charged particles around, this is almost entirely backwards analogous to Faraday's law. Faraday's law, you have a changing magnetic field that gives you an electric field. Here you have a changing electric field that can give you a magnetic field. And in fact, in some ways, changing the electric field has the same effect in terms of the magnetic field as a current would. That's kind of cool. In fact, we call this term right here, epsilon naught d phi e dt, a displacement current. What is being displaced and how is it like a current? That may be clear when we do an example. So let's set an example up and do something very similar to what we did last time. Last time we wanted to set up a uniform magnetic field and then change that magnetic field to induce an electric field. Now we want to have a uniform electric field. We want to change that electric field to induce the magnetic field. To create our uniform magnetic field, we had a coil. How are we going to set up a scenario where we have a uniform electric field that we can vary? What kind of device would that be? A capacitor. Exactly right. A parallel plate capacitor. If you have two parallel plates and you apply a voltage between them, charge will build up on either plate, and between the plates will have a uniform electric field between those two plates. That's a capacitor. Now, I still don't have access to move this thing down, but that's okay. So let's draw a parallel plate capacitor. I'm going to draw it pretty big over here. There's one big circular plate seen from the side. There's another big circular plate seen from the side. We'll connect them by some sort of wire. We'll even put a voltage here so that we can apply a voltage between the two of them and charge that capacitor up. Okay. Let me put some numbers in here, just so that when we get to the final equation, you can plug those numbers in and see that it kind of worked. Let's say it's a circular capacitor. Let's say R, the radius of that circular capacitor, is 10 centimeters. This is a big thing. Like, this is going to be a capacitor that's macroscopic size, like that big. Let's say the D, the distance between, so let's actually put these in here. There's R. D is going to be the distance between them. Let's say that's much smaller, a millimeter. I have vastly drawn the distance between these two. Let's say it's a millimeter. Let's say our initial voltage between these two is 200 volts, which is pretty big. And let's say, again, if we just have a voltage of 200 volts on there, we're going to have a uniform electric field, but we won't have an induced magnetic field because we need a changing electric field to get that magnetic field induced, right? So we're going to have to discharge this capacitor. You did a lab in Inlet 2 where you discharged the capacitor and had, you saw that it was an exponential decay. Let's say we discharge this capacitor, though not in a just normal way. but in a controlled way such that the voltage drops linearly over time. That's going to be much easier for us to deal with. So this is discharged over some time. Let's say delta t equals 10 milliseconds at constant voltage. Okay, so we know where is that current flowing when we discharge this capacitor? Is it flowing through the plates, between the plates? No, it's in the wire. That's where the current is. So we know from the first part of Ampere's law that will induce a magnetic field near the wire. The second part of Ampere's law, the Maxwell's induction part, tells us that there will be an electric field here with the voltage up, and that as that voltage changes, we will also get a magnetic field in between these two plates, even though no current is actually flowing through it. This is kind of what he means by displacement current. It's almost as if there is current flowing through those two capacitors. It works very much the same way, behaves very much the same way as a current in inducing a magnetic field, even though no charged particles are actually moving between those two. Okay, so to extend our page, we're going to need some more room here. We know that I is related to Q, the charge on each plate, by dq dt. So if we decrease so if the current is constant, then the charge decreases at a linear rate. Great. We also know from parallel plate from all capacitors that the charge on the plates is equal to the capacitance of the capacitor times the voltage. So we know that if the charge is decreasing at a constant linear rate, that the voltage is also decreasing at a constant linear rate. V also goes down linearly. There we go. Uh-oh, did I start the wrong one? Oh, I did. That's so sad. Shoot. Well, if you know anybody who is zooming into this, oh, here comes somebody. If you know anybody who was trying to zoom in, give them my apologies and let them know that we're on now. Hey, Noah and Scott, sorry. I actually started the Zoom meeting, but it was the wrong session, so you weren't able to get on. My apologies.
No worries.
I think I took a video of it. I'll post the video. Basically, we're working through an Ampere's law problem with the added term from the greatest hits of Analyte 2 sheet. So we've set up a parallel plate capacitor. I didn't even draw this, but there's some electric field, uniform electric field within this capacitor. And we're trying to determine now what the induced magnetic field will be inside that capacitor. So here we go. Okay, so what is the voltage going to look like? What is voltage as a function of time going to be? Again, we have set it up to some constant voltage, and then we're going to let the current discharge this capacitor over time in a linear fashion. So it'd be nice to have an equation for V as a function of t. It's not a hard, it's a linear equation. It's a linear equation. There is some constant term, and then you get 1 t over delta t going to look something like that. V as a function of t will start out at t equals 0 at some v naught, and then over some period of time, decay to 0. Right? So that's what we expect V as a function of t to look like, the voltage, until it reaches 0, and then this equation no longer works. But we don't care about once it reaches 0, actually. We're only interested in while it's decaying from V naught to 0. We can also, they may remember the electric field of a parallel plate capacitor from the voltage. I never remember these formulas, so kudos to you if you do. I always have to look them up. It is simply the voltage divided by the separation of the plates. Okay, so let's consider we want to know what the induced magnetic field is for some point between the plates, right? Which point? I don't know, let's call it this point right here, maybe. This and now almost is completely analogous to the situation that we went through when we did an Ampere's law problem, or did a Faraday's law problem. We need to think about the flux, and so we're going to make an assumption that the induced magnetic field is going to be constant at a given distance from the center of this capacitor. It's an electric flux, so we're going to assume that a circle of radius 0 is going to be 0. There should be 0 induced magnetic field right at the center of our capacitor, and it probably will increase as we go out in some linear way, or in some way. So if we take a loop that is at some distance r, let's say, little r from the center, we can take a loop inside there where all those points have the same distance r from the center. And this will give us all the advantages that we got for the surface that we drew last time as well. So, so draw a loop between capacitor plate, between the plates of radius r.
Hey, Dr.
So let's say that r is less than the big R, the actual, so we're not only between the capacitor plates, we are within the radius of the capacitor plates themselves. Okay, what is phi E then in this case?
Professor?
Yeah, go ahead, Scott.
Can you, right now we can't see the screen you're writing on.
Oh, yeah, I forgot to, thank you. He can't see my screen. You guys couldn't hear him, but he can't see my screen. And the problem is I haven't shared it with you. Oh, you know, thanks for pointing that out, Scott. How about now?
Yeah, we can see it now.
Okay, great. Sorry about that. Okay, so let me just scroll up so you can see this. We've got a parallel plate capacitor here of radius capital R. We've just drawn a loop inside of it with radius little r, and we're going to think about what the electric flux is between that, from that loop, right? Flux is defined to be, and this is a crazy definition which you almost never have to really deal with, the electric field times the area vector integrated, right? This becomes extremely simple though, because our area vector is parallel to our electric field vector in this particular case. So that dot product becomes a vector becomes a regular product of the magnitudes of those vectors, which is much simpler. This is just the integral of E times A dA. And since E is constant over that whole loop, you can pull it out of the equation. This is just the E times the integral of dA. And that is just E times A. So if you set your loop up properly, the magnetic flux is simply nothing more than the electric field times the area of the loop that you've drawn. Okay, great. Which is, in this case, E times pi little r squared. Great. So we've got a d phi dE term in the right-hand side of our equation, d phi e dt. This is ddt of this whole thing, right? But pi r squared, let me just write it out. This is ddt of e times pi r squared. Pi and r aren't varying with time though, so we can pull those out of the derivative. This is simply pi r squared times dE dt. Great. And so the entire right-hand side of our equation is simply mu naught times epsilon naught times pi r squared. Oh, wait. Sorry. Got ahead of myself. Right. But we really have is the voltage. And so we need to turn this E into a voltage. But that's not hard to do because we know how E is related to voltage, right? E is simply the voltage divided by D. So this whole thing then is pi r squared over D times dV dt. Since D isn't changing either. You can pull that out of the equation. And V, we know how it depends on T. We have a function for V as a function of T. We can just plug that in. That's V naught times 1 minus T over delta T. Great. That's a pretty simple derivative. This is pi, oh, I've got the ddt. This whole thing taking the time derivative of that voltage. We get pi r squared over D. ddt of this thing, you've basically got two terms, a V naught and a V naught T over delta T. The V naught's constant, that's 0 when you take the derivative of it. The second term is linear with T, that's really simple. The derivative is simply the term without the T in it. This becomes negative V naught T over delta T. So this is right. Sorry, the T isn't on there, you're right. T went away. It's just V naught over delta T. Thank you, you're right. So the whole right-hand side is just d phi e dt times mu naught epsilon naught. So the whole right-hand side is mu naught times epsilon naught times pi r squared over D times V naught over delta T. And the negative sign here cancels out with the negative sign that was in there to begin with. This is very similar to what we did yesterday with the looped coil. How about the left-hand side? Left-hand side is loop integral of B dot ds. Again, this is a loop around the outside of the circle that we've just drawn, right? So again, we're going to hope that this B field is going to be always tangential to the loop we've drawn. And we're going to hope that it's constant around that edge by the symmetry that we've drawn. And those give us exactly the same advantages as the flux integral gave us. The parallel means we can do a regular product instead of a vector product. The constant means we can pull it out. And this really is just the magnitude of the magnetic field times the circumference of that loop, which is 2 pi r. So we can just set these things to equal to each other now. B times 2 pi r is equal to mu naught epsilon naught times pi r squared D over D times V naught over delta T. And you can solve this for the magnetic field. Just pull your 2 pi r over and you get mu naught times epsilon naught times r over 2d times V naught over delta T. The pi even goes away. And when you plug in the numbers that we put in above, you get a number that's something like 8 times 10 to the negative 12 Tesla. and it's constant over the period over which you're discharging this capacitor in a linear way. That will be the induced magnetic field that is set up inside your capacitor, and it will be constant as long as d phi de is constant, as long as you're discharging that capacitor in a linear way. Okay. This isn't a very big magnetic field. It's pretty small. We got a pretty big area, but that's okay. This is the only geometry we're ever going to worry about in this class. You need very powerful math tricks to be able to solve problems using geometries that are any more complicated than this. And upper level E&M classes turn into a series of math tricks that you use to be able to solve more and more complicated problems. We're not going to worry about any of that. Yes, Bailey. Oh, question?
Right, so this is just the displacement current, right? This would account for like the current running through the actual capacitor.
So the question is, for those zooming in, this is the displacement current and not the current running through the capacitor itself. There is no current running through the capacitor, right? So both of those terms are right in the equation. The I term specifically is 0 in this particular case, but you get a term that looks like a current from the d phi e dt term, right? So displacement current isn't a real current. It is the thing that is on the other half of that equation that kind of acts like a current and does the same sort of thing. You get these looping magnetic fields around your device, but it's not from any physical current that's actually passing through your loop. The physical current passing through that loop is 0. But that changing magnetic field, the changing electric field acts just like a current would. And in fact, if you were to do the same problem and were to define your loop to be outside the radius of this capacitor, you would find that it would not be possible to distinguish the difference between the displacement current and the regular current. It would look just like a current of I were passing right through that spot as well, which is kind of cool. Good question. Any other questions? Yeah. Yeah, no, I think I messed that equation negative sign up. It doesn't really matter. Yeah, it's a positive sign there. You're right. It just doesn't go away. I realized that after I did it, that negative sign doesn't actually go away. So the right-hand side, there really is a negative sign here. It doesn't go away. This is technically a negative sign. What does that negative sign do? It just tells you the direction that B field is propagating. It's the right-hand rule negative sign. So in terms of the magnitude of the magnetic field, it makes 0 difference. It's going to tell you which direction it's propagating around the current. Thank you for pointing that out, though. That's true. That should have been a negative sign there. Yeah, big R, we didn't define it. And that's the cool thing about this, right? What does that mean? We defined big R. So the question for those Zoomers were, how did we define little r? What is the value? Oh, that's true. I put in some numbers and didn't tell you what the number was. That's a good point. There's a bigger point here, though. And the bigger point here is we defined a big R. It doesn't really matter what little r is. We have developed an equation that gives us the magnetic field at any little r. We can plug in any little r to that equation and get what the big B field is. You're right, though. The number I wrote down had to have had a specific value of little r. Probably halfway out. That's usually what I do with these things. That's a good question, though. But it doesn't really matter. In fact, the number isn't even all that important. The number is far less important than this equation, which gives you the magnetic field at any little r. Any little r, that is, until you get to the edge of the real capacitor. And then the story actually changes a little bit. It's a different equation after this because the magnetic flux, the electric flux won't change anymore as you get bigger and bigger and bigger, but your loop integral will get bigger and bigger as you keep going out. So there are some problems in future homeworks where you have to think about those things. Other questions? Excellent. Okay. All right, on to the reason why we're bringing all this stuff, all these painful memories from Analyte 2 back in the first place. And that is that we want to use them to do something new and unique and different and interesting. And that new and unique and interesting and different thing is electromagnetic waves. Okay, so let us consider a region of space that is free of all charge. We're going to consider a universe that is empty. How does that affect our Maxwell's equation laws? Let me bring them back up. How does that affect Maxwell's equations laws if we're in a region of space where there are no charges? What modifications are you going to have to make? Or what simplifications are you going to have to make? It makes your life a little easier. What terms go away? The Q term goes to 0, right? You've got a Q term in Gauss's law. Integral of E dot dA equals 1 over epsilon naught Q enclosed. If you're in a region of space where there's no charge, Q enclosed is always 0. So that term becomes a 0. Great, what else? The current also goes away. There, if you have no Q, you have no I, and therefore I is always 0. So the version of these equations where you have no charges, your physical region of space with no charge, you can write them down thusly. So let's say region of space with no empty. No charges. So let's write these equations down. Gauss's law becomes E dot dA equals 0, which is entirely the same, analogous to Gauss's law for magnetic fields, which is B dot dA equals 0. Faraday's law doesn't change. It's just E dot ds equals negative phi b dt. And finally, Ampere's law becomes B dot ds equals mu naught times epsilon naught times d phi e dt. They are very symmetric now. In fact, the only reason why there were asymmetries in Maxwell's equations was because we had point charges for electricity, but we don't have point charges for magnetic fields. Once you take out the point charges for charge, then they do become completely symmetric and analogous, which is kind of cool. So, are there patterns of fields that satisfy all 4 of these equations at the same time? That's what we're really interested in looking for. Patterns of fields that will satisfy all of these equations simultaneously. They're going to have to be time varying fields, right? Otherwise, we're just going to get nothing happening, nothing interesting happening at all. There's no way to get these fields propagating or existing for any period without them being time varying, because the only place where there's non-zeros on one side of this equation is with time derivatives of things. So in order to solve this, we would really need to turn these into differential equations and do the differential equations. Now, most of you are still just starting calculus 3. You're not, even if you are doing the differential equations, you're probably just starting differential equations. So we're not really gonna dive full bore into solving these equations, but I do want to give you a little flavor of how differential equations work and why they're useful, and maybe lead you to an answer here before we get too much further. So let's walk through how we would solve these differential equations without actually solving the differential equations. So let's think back to a problem that you are probably more familiar with and have spent some time with, and that is a mass on a spring. So we can write down a force equation for this spring. Usually you will write, so let's say you've got a spring there and it's standing there in equilibrium and you're good to go, and you pull it out of equilibrium. Let's call x equals 0 your equilibrium point. I'm going to pull it out of equilibrium a little bit. The force that is exerted on that mass is negative kx. K being the spring constant and x being how far you've displaced it from its equilibrium position, right? That should be, right, x equals 0 is equilibrium. Great, but you also know that force is mass times acceleration. So mass times acceleration is negative kx. But you know that A is dv dt, and v is dx dt. So A is really the second derivative of x. Right? Second time derivative of x. The first time derivative is the velocity, the second time derivative is the acceleration. Okay, so this gives us this equation. M times d squared x dt squared equals negative k times x. And this is some x of t, right? X is going to be changing as we go along. This is a differential equation. It's got x on both sides, right? Calculus 1 doesn't teach you how to solve these kinds of equations. But what is this? That's confusing. But so this is how all differential equations work. You get an equation like this, and you try to come up with a solution that will work. Some function of x where you take two derivatives of it and you get the negative of the function back. Can you think of a function that you take two derivatives of it and you get the same function back but a negative of it? Sine, the sine function, the cosine function. Take the derivative of sine, you get cosine. Take the derivative of cosine, you get negative sine. That is a function for which you take two derivatives of it and you get the function back again, negative. And sure enough, what's going to happen when you pull that spring down? Doing, going, going. It's gonna bounce up and down in a sine wave. It works. And the cool thing about, you'll learn this, the theory behind why this isn't in differential equations. Once you find a solution to a differential equation, that solution is unique. That's cool. So we did it. We solved the equation. It's not really sine x. You've got to have some variables in there to make the k and the x work, k and the m work. But it's basically sine x. You can figure out where those constants go inside the sine to make it work out. Sine was the hard part. Cool. This is similar to the situation we've got here. Let's think about what we've got here. We're going to take a time derivative of a magnetic field and get an electric field. We're going to take, actually, let's do it this way. We're going to take the time derivative of an electric field and get a magnetic field. Then we're going to take the time derivative of the magnetic field and get the negative of the electric field. It's basically exactly the same thing we had in our spring problem. We should guess, we're going to make guesses and see if they work. And I'm not going to lead you astray. The guesses will be pretty good. But those guesses should involve signs for the very reason that we've just seen up here. We need to take two derivatives of something and get back to that something but negative. This is always going to be sines and cosines. Okay, let's try these equations. So back to electromagnetic waves in a vacuum without any particles around, in empty space. Let's try solutions to the equations that look like this. These are much more complicated, right? We've got two of them. These are vector quantities. And so the geometries are a lot more complicated than our simple mass on a spring, but that's okay. Let's just try this out and see what happens. The electric field is equal to some maximum electric field, which is going to be the amplitude of our wave, times the j hat vector times the sine of kx minus omega t. And the B field is going to be some, again, maximum B magnitude in the k hat direction times the sine of kx minus omega t. This is clearly a wave, right? In which direction is this wave traveling? Say it again. Huh? J, yeah. X, Y, or Z. In the Y direction? Why do you say the Y direction? Okay, so you're good guesses. Clearly, the j hat is in the y direction. The k hat's in the z direction, right? However, you're setting your vector point up. How do you know what direction the wave is propagating in? Now, the electric fields are pointing in the y direction, whatever the y direction is. Let's say up. The magnetic fields are pointing in the z direction. Which direction is this wave traveling in, and how do we know? Why? Okay, you're right. You're right to be thinking about cross products. We have not yet defined the property of this wave that E cross B is in the direction of motion. It is, and that's a good way to think about this, but you should be able to look at these equations and immediately should know which way these things are going. It is a function of X. The fact that X is in the sign tells you that it's moving in the X direction. It has to be. That's the way things are changing. They're not changing at all in Y or Z. In fact, what have we got here? We've got an infinite wave propagating in the X direction. The value of that wave in all Y points and all Z points is exactly the same. The only difference is in the X direction. And it changes over time at a given point, but it only changes at a given time in the X direction. Is it moving in the positive X or negative X direction? And how do you know? How do you know? It's the negative sign in front of the time. The same reason why the sign equation that we wrote down last time had to be moving also in the positive x direction. So this x here tells you that it's moving in the x direction. This negative sign in front of the t tells you that it's moving in the positive x direction. Why wouldn't we set, we have the option to set our coordinate systems up any way we want to. Why wouldn't we make it go in the positive x direction? That's the logical choice to make. But you should be able to look at an equation like this and immediately know, okay, that's a wave moving in the positive x direction. So that's an intuition to build up as you're looking at these equations. Okay, some properties. Let's look at some properties of these. These two waves that I've just put down. E and B, the direction of the E and B current fields are always perpendicular. E is in the y direction and B in the z direction. Okay, E and B are always in phase. You notice that there is no phase constant with either one of these. It's 0. You notice that the frequencies are exactly the same for all of these two. So the electric field and the magnetic field are varying in time, but they're varying in phase. When one's at a maximum, the other's at a maximum. When one's at a minimum, the other's at a minimum. When one's 0, the other is 0. And this is what you were talking about before. E cross B is in the direction of propagation. So at t equals 0, E is pointing in the positive y direction. B is pointing in the positive z direction. Y cross z should give you a pointing in the x direction vector. And that's true even when both of them will go negative, it still points in the positive x direction because they both turn around at the same time. And as time progresses, this wave moves. Fast, in fact. Okay, let me show you some PowerPoint slides. Oh, look, here were some things. Oh, there's a better picture of our parallel plate capacitor. This is online. You can download this PowerPoint slideshow and get a better view of this. Here is what we've got for our magnetic field. This is what it looks like traveling down, traveling through space. You've got the axes are set up differently than I have, so you can ignore the axes. I apologize for that. But E cross B has to be moving in the V direction, and so you get always these are perpendicular to one another. And when one is positive, the other is positive, and one's negative, the other is negative. This is a pretty good way to think about this. So here it is. You can actually watch the wave progress now as you go through, right? I know, it's crazy. Here's another one from the side, seeing the same thing. So, I want to pause by giving you some lessons about and some intuition about magnetic fields and electric fields. It looks like there's spikes coming out and up and down from this line. Those spikes are indicative of the strength of the magnetic field at that point. These spikes don't actually stick out anywhere. There is no physical thing that's sticking out. If this were a single line of magnetic field, an electric field, and you were to put a circle above it, it would look like some of those magnetic field lines are poking through your aperture. They are not actually poking through your aperture, right? They are simply representations of vector quantities defined along the line that you're looking at. These don't physically poke out in any meaningful way. They're just representations of how big the quantity is that vector is at that point. Kind of like velocity and acceleration. They don't physically point out anywhere. But since we talk about things like electric flux and magnetic flux, we can get confused when they're pointing in that direction. Don't be confused by that. And this is but this is happening everywhere, right? You're seeing the representation of a single point, but the fact is this is happening at all x and y points simultaneously. It's a plane wave propagating through from one direction to the other. All points in the xy in the yz plane have the same values of electric and magnetic field at a given moment in time, pointing in exactly the same direction. Does that make sense? Okay. Quick note: we're done with class today. We're going to start class. We don't have class on Monday because of Labor Day. Enjoy your 3-day weekend. I'm going to post a homework set this afternoon. That homework set has 2 sections. One of them is a written section and one of them is a Kappa section. The written section you should not do until Wednesday. I'm going to be doing some examples in class that are very helpful for the written part, where I ask you to prove that Gauss's law and Faraday's law work for these particular sets of equations. So that will be due Friday. You'll have a couple of days to work on it even after Wednesday's class. You should be able to do most of the other problems on this set, but save the written problems for next week. Okay, have a good weekend.
Dr. Steinhauer,
Yes.
did you mention anything at the beginning of class about the quiz, the reflection quiz on Canvas?
I did. Sorry, I'm talking. It's due at 8 o'clock tonight. The Kappa's due at 5. It shouldn't take you more. And I sent you an email about this too, Scott. A couple of sentences, a paragraph for each is fine.
Okay, awesome. Thanks so much.
Is that what you're wondering?
Yep,
Or is that
basically.
Noah? That's Noah, not
Yeah,
Scott.
it's Noah, yeah.
Sorry. Okay, I sent Scott an email. Okay.
Okay.
Cool.
And so when will all the notes and videos of you be posted for this class?
I will post the video as soon as I get it. I'll post it this afternoon.
All right, sounds good.
All right, and if you need the notes, let me know. Sorry about that.
No, yeah, you're fine. Don't worry about it.
Okay.
Thank you.
All right, thanks, Professor.
Like this on possible, and it could just be with the like we're only doing the specific loop, but then I just don't understand where big R comes into play at all.
Big R would come into play when you're actually calculating the capacitance of the capacitor itself. This R, again, so this R came from the flux through our aperture that we drew. And our aperture that we drew was little r. This R is the loop around the loop that we draw. That's just the distance around. That's the circumference of it. The big R would come in when you are calculating the capacitance of the capacitor itself and what that voltage is and how it's changing. So there will come a time when there will be a big R in here, but that's when I'm asking you, hey, a capacitor that has this capacitance or this physical size, and you have to calculate the capacitance, and that R will fit into it. So there will be big R's that come in. And the other way big R's can come in is if you draw your loop bigger than the capacitor itself, the loop integral is still little r, but the flux integral is only over the place where there's actually electric field, and that's big R. So you stop, even if you make your loop bigger, the flux isn't increasing anymore once you get outside the edges of the capacitor. So that actually stops and becomes a constant.
So the max is big R.
Right.
Do you know what chapter we are?
It's on, I actually put it on the syllabus. I don't remember. 30 sounds right though. Electromagnetic wave. It's certainly on the syllabus, and if you need, I don't remember the top of my head, but you can send me an email if you can't find it. Okay. All right. So confused, it didn't make any sense. Okay.
This number.
Um,
I couldn't read it. 'Cause it's in the back.
Okay, that's just straight Top Hat. If you're in the Top Hat class, I'll actually send out an invitation maybe this weekend if you haven't already joined the class.
I think I am.
Okay, so just open your Top Hat app on your phone and click I'm here, and I think that's all you need. And that number is really for people who don't have smartphones, so you can text it in.
Okay. What's this? Never joined for the. Yeah, I'm in it. Nothing's there.
Right. I closed the attendance after a couple minutes because it was just taking up space on my screen.
Oh, okay.
Don't worry. That attendance is purely for, it's good to know that you're here. That attendance, though, is not, I'm not going to use it for any grading purposes or even look at it. It's if somebody in here tests positive, the provost would like to know who physically was in the room every day. So I'll have that open at the beginning of every day. Just open your phone, say I'm here, and that just helps. Then I can provide a list to the provost if somebody tests positive of who was actually in class.
Yeah.
Make sense? Yep, thank you.